Bismillahirrahmanirrahim. Assalamu alaikum students. Today we are going to discuss the idea of phase space. What is the phase space? If you take into consideration the Newtonian formulation of mechanics, in Newtonian formulation, position and velocity of a particle specifies its state. That means if you know at a particular time the position and velocity of a particle, then you can predict its position and velocity at any future time using Newton's laws of motion, this Newtonian mechanics. That means if I have a single particle, each pair of the value of position and velocity specifies its state, and all pairs of positions and velocity are different states. If you change position, state changes. If you change velocity, state changes. If you change both, then state changes. Now, if you know state at a particular time, you can find the state at any future time, or you can also find the states through which it have arrived to that particular state, right? So, state is specified by position and velocity in Newtonian mechanics. Then you know, when we talk of Hamiltonian mechanics, in Hamiltonian mechanics or Hamiltonian formulation of mechanics, I should write Hamiltonian formulation of mechanics. What we do, as you know, Hamiltonian of a system is function of position, generalized position, then we talk of generalized momentum, and in general time. So in this Hamiltonian formulation, state is specified by position and momentum, not position and velocity. You know, from Hamilton's equations of motion, we can find q dot and p dot. Q dot being the time derivative of position and p dot being the time derivative of momentum. We are talking in generalized coordinates here. So if we know the position and momentum at any time, we can find the position and momentum at any future time using Hamilton's equations of motion. So every pair of position and momentum specifies a state in Hamiltonian mechanics. Now, why it is advantageous over that situation when we talk of position and velocity as specifying the state? Because you know, when we go to quantum mechanics, there we have Heisenberg's uncertainty principle, and position and its corresponding momentum become the conjugate variables. There is restriction on the degree of accuracy with which we can simultaneously determine position and momentum of a particle. So, when we see the Hamiltonian formulation, it is repackaging of mechanics where position and momentum describe the state of a system. It is easier for us to put the limitation on this position and momentum using, or you can say on this state specification using this quantum mechanics. So, going to quantum mechanics using Hamiltonian formulation, specifying the position and momentum as using these variables as state specification variables, going to quantum mechanics becomes easier for us. So what is now this phase space? Phase space is this position momentum space. For example, if we consider a single particle moving in one dimension. So consider a single particle moving in one dimension. Let the dimension be x. Now I can specify its states by making two coordinate axes, one denoting position x and another denoting its momentum. Now this two-dimensional space, one axis is specifying its position and one axis is specifying its momentum. This becomes phase space for this particle, because every state will be specified by a point. For example, if I consider some point in this space, two-dimensional space, then this will specify the state of this particle. If you take another point, that is another state. Now why we use this word phase? Because it is due to Gibbs. When state changes, he uses the word for that, phase changes. So phase change is synonymously used for state change. So in this phase space now, situation is like this, that each point in this space is a collection of two numbers, that is one position and one momentum, that will specify the state of this particle moving in one dimension. And if you know this point representing its state in the phase space at a given time, you can find where it will go or where from it has come. That means which states it is going to acquire in future time, or which states it has already acquired in past time, using Hamilton's equations of motion. That means the specification of the state at a particular time is enough to determine all the possible states in future using laws of mechanics and all the states in past. So this is the idea of phase space. Now see, we can divide this space into small cells. For example, if I do it this way, so you make divisions of this phase space into these cells. Now let the width of the cell along position be delta x. Let this be delta x, and let the width along p axis be delta p. Then the area of each cell is delta x delta p. Now in classical mechanics, there is no restriction due to Heisenberg's uncertainty principle. That means you can arbitrarily decrease the width of this cell along each side. That means delta x can be arbitrarily small in classical mechanics, delta p can be arbitrarily small. Therefore this product, which I denote by h naught, which is the area of each cell, or you can say it is the two-dimensional volume, which is the area of the cell. This area of the cell can be arbitrarily small. So in classical mechanics, this h naught can be arbitrarily small. You can make it so small as you like. There is no restriction. So, incidentally, what are the dimensions of this h naught? The constant, it will have the dimensions of angular momentum, because it is linear momentum times the distance. Now another thing, when you locate the state in the cell, you are actually specifying its position in the cell, means you are specifying its state. Now if I say the particle is somewhere in the cell, that means I am saying it can acquire any state or any point lying in that area in this case, right? Now in classical mechanics, as I told you, delta x can be arbitrarily small, delta p can be arbitrarily small, so you can pinpoint the position or and the momentum. Hence you can make the cell as small as possible and specify the position and momentum simultaneously with arbitrary accuracy, right? Now when we generalize the idea of phase space to in generalized situation, if we have f degrees of freedom in a system, this was a single particle moving in one dimension, but if I have a system in general where I have f degrees of freedom, that means I have generalized coordinates q1, q2 up to qf, and then I have corresponding generalized momenta p1, p2, p3, and similarly up to pf. So this is my system with f degrees of freedom. It is understood that these generalized coordinates are the minimum number of coordinates required to specify the system. You know that the minimum number of generalized coordinates required to specify the system is the number of degrees of freedom in the system. Now for this system, if I have a system of particles where there are f degrees of freedom, then I want to construct the phase space corresponding to this system. Now this space will have 2f rectangular axis. You can see when I have one particle in one dimension, then the phase space is two-dimensional. One dimension is corresponding to position, another dimension is corresponding to momentum. But if I have a system with f degrees of freedom, here you will have one coordinate axis corresponding to q1, one corresponding to p1, one corresponding to q2, one corresponding to p2, and similarly for each q1 and for each p and for each q, you will have a rectangular coordinate axis. So this phase space corresponding to f degrees of freedom will be 2f dimensional. 2f dimensional space. It is understood you cannot visualize such a space because we are restricted in this routine life with three-dimensional space, right? So you cannot visualize it, but you can conceptualize this space where you have 2f coordinate axes perpendicular to each other, right? Now each point in this space will be collection of all q's and all p's. That means each point in this 2f dimensional space will be specified by 2f numbers. 1f corresponding to the coordinates and 1f corresponding to the momentum, right? So that collection of 2f numbers is specifying state in this 2f dimensional space. Here we had two-dimensional space for one particle in one dimension. So one point was pair of two numbers. Here one point in this space which is specifying the state of the system, there will be 2f numbers corresponding to each point. 2f numbers are specifying the state in this 2f dimensional space, right? Now, how we find the volume of the cell in this 2f dimensional space? Now, this will be written as delta q1, delta q2 up to delta qf, then delta p1, delta p2, similarly up to delta pf. What is this? This is actually the volume of the cell in this 2f dimensional space, because it will have 2f edges. Delta q1 is the edge of this volume along q1 direction. Delta q is the edge length of this volume along q2 direction, and similarly when you multiply space. So it is volume of the cell in this two-dimensional, 2f dimensional phase space. Not two-dimensional. It is the volume of the cell in this 2f dimensional phase space. Right? Now, if I divide this space into equal areas pertaining to each coordinate and corresponding momenta, that means if delta q k times delta p k is h naught, that means if I take some generalized q and take edge length along that and corresponding momenta, then take edge length along that, I multiply that, I will get the area of that piece, that is h naught, and if I make that area uniform for all q's and corresponding p's, then this volume can be written as h naught raised power f, because there are f degrees of freedom here. So this h naught raised power f becomes the volume of this phase cell in 2f dimensional phase space. Now this equation, which we wrote for the area or two-dimensional volume for the phase space which is two-dimensional, is contained in this equation. If you write f is equal to 1, it is 1 this degree of freedom system, it will reduce to this. Then you will have only one delta k and one delta p. Right? So this is how we write the volume of the cell in 2f dimensional phase space. Incidentally, you can notice this, whenever you construct this phase space, it will be even dimensional. If I have 1 degree of freedom, then it will be 2 dimensional. If I have 2 degree of freedom, then it will be 4 dimensional. If I have 3 degree of freedom, then it will be 6 dimensional. Because for every corresponding to every generalized coordinate, there will be a generalized momentum. So it is always even dimensional space. It is never odd dimensional space. Now one more thing, you know, from Heisenberg's uncertainty principle, we have a restriction. In Heisenberg's uncertainty principle, we know that we cannot specify the position and momentum of a particle simultaneously to the arbitrary accuracy we like. There is a restriction on the degree of accuracy with which we can simultaneously specify the position and momentum of a particle. How we write that? We know delta q, delta p is greater than or equal to h bar by 2, where h bar is h by 2 pi, h is Planck's constant with value 6.6 into 10 raised power minus 34 joule second. This is the Heisenberg's uncertainty principle. If you know the generalized position and corresponding generalized momentum, then this product cannot be arbitrarily small. It can be at least h bar by 2 or more than that. So you have a restriction. Upper limit you can go anywhere for this product, but lower limit it can at least be h bar by 2. That is h by 4 pi overall, where h is the Planck's constant. So that restricts the volume of the phase cell in the phase space. When you take this into consideration, then you cannot make the cell in the phase space arbitrarily small. You have this h naught can be arbitrarily small. This h naught can be, its smallest value will be h bar by 2. So this is the nature of the phase cell or phase space when this is taken into consideration using quantum mechanics. In classical mechanics, there is no restriction on h naught, it can be arbitrarily small, but in this quantum mechanics, there is Heisenberg's uncertainty principle. H naught can be at least h power by 2. Another thing you need to remember, you know now, for any classical system, we specify state by specifying its momenta and position. Then in the corresponding phase space, a point in the space will specify the state completely. At a particular time, if we know which point is representing the state, we can find the trajectory of the particle or system of the particles in the corresponding phase space by using laws of mechanics, for example by using Hamilton's equations of motion. There is another thing called ensemble. What is ensemble? Or I should say statistical ensemble. What is statistical ensemble? For example, if I have some glass containing 3 dice, I have a glass containing 3 dice. You know dice? When you throw a dice, you can have 6 outputs. 6 outputs mean its uppermost side can be 1, that side which has labeled point 1 dot on it, then its one edge has 1 dot, its another edge has 2 dots on it, its another edge has 3 dots on it, its another edge has 4 dots, then you have 5 dots on the edge, and it has overall 6 edges. So another edge has 6 dots. So when you throw a dice, you can have these 6 outcomes. Now if I have a glass, I have 3 dice in it. Now I throw this glass on some table, I can have multiple possibilities, I can have multiple outcomes. You can calculate them. It will be, for example, it will be 6 raised power 3 total outcomes if you check it. For example, for each the dice there are 6 outcomes, another dice 6 outcomes, another die 6 outcomes. For this system of 3 dice, you will have 6 raised power 3 outcomes possible. Because the dice are distinguishable, you can specify which dice we are talking. You can place, for example, some plain dot on the dice, and for example on one dice you label green dot, another red, another yellow. Then you can talk this way, that you can say the dice which has yellow dot on it has this outcome, red dot has this outcome, green dot dice has this outcome. This way, once you have established that these are distinguishable dices, you can label them, then you have overall outcomes in the system. You have 6 raised power 3, right? Now this is my system. This system of 3 dice in the glass is my system. Now I want the outcome. When I talk of these outcomes, they are many. 6 raised power 3, and if you increase the number of dice in the system, automatically the number of outcomes which you can get when you throw this system of dice increases. Now classical mechanics can predict the outcome, but the issue is the number of variables in the system to obtain the outcome in the system of these dice is number of parameters are so much large that your information is too much to digest in classical mechanics, because you have to check which dice is which way oriented when this glass is set into the throwing situation. You have to first see which state is occupied by each dice, how dice is placed in the glass, right? So predicting the outcome on the basis of classical mechanics, for example using Newton's laws of motion or Lagrangian formulation or Hamiltonian formulation to each dice and predict the outcome, becomes difficult because the number of input variables is large, is huge, and that number grows as the number of dice in the glass increases. Now what we do then? We have a statistical method. What we do, we have a statistical method where we construct an ensemble of systems. Ensemble of systems means you imagine a collection of systems, collections of systems of identical structure. By identical structure I mean, you imagine you have many glasses which are identically constructed. For example, if I have 3 dice, I have placed these 3 dice, similar dices, they must have similar composition, similar edge length, similar smoothness, everything should be same, and they must be placed similarly in these glasses. So I imagine I have a collection of systems having identical structure. So to predict the outcome of this system, this is my system of interest. This is my system of interest. I want to make predictions about the system. Now what I do, I imagine or conceptualize an ensemble, a collection of huge number of systems which have identical structure, and focus attention on their outcomes, right? So to get the outcome of the system of interest, I imagine I have many such glasses, many such systems identically constructed, as if I throw all those systems simultaneously and check the outcome in each system of the ensemble. Then what I do, I take the average of the behaviors of the systems in the ensemble to predict the behavior of the system of interest, right? So we have some system of interest. The variables are huge, their number is huge. So classical mechanics, using the laws of motion to each particle or component of the system is not possible because the number of variables is huge. Then what we do, we imagine an ensemble of systems which are identical copies of the system and average the behavior of those systems to predict the behavior of system of interest. Now it is not just now in this system of dice. You can have a container of gas having certain gas molecules in it, and you have some pressure, some volume, some temperature of this microstate of that system. Now to predict its behavior, you construct the identical systems, large in number, right, and predict the behavior of the system of interest by averaging the behavior of all those systems in the ensemble. Now when we talk of phase space, then we talk of the position of the system. Now position of the ensemble of the system in each ensemble. If you take some ensemble of systems, now the state of each system in the ensemble will be specified by a point in the phase space. And if you want to see the situation of the ensemble as a whole, then you have a collection of points, cloud of points in the phase space. That means corresponding to the ensemble, you will have a collection of points, that is a cloud of points in the phase space, and corresponding to each system in the ensemble, you will have a point in the phase space. I stop here. I think this is enough for today. Next time we will continue this lecture. So today we discuss the idea of phase space. We discuss the restriction of quantum mechanics on the cell size in phase space, and we talked about the idea of ensemble. Thanks for today. Inshallah, we will meet next time.